general relativity, step by step. Last time I worked out the alpha component of the divergence of this vector field and showed that it was equal to 0. And now what I'm going to do is extract just the beta components. I got myself all tangled up when I tried to do everything together, so that's why I'm separating it up into alphas and betas. So the first one is di by di theta. What colour am I? Yep. Okay, so the first bit is this bit here, which is di by di theta of beta h minus 1. Di by di theta. This is the beta component of beta h minus 1 cos squared. Beta h minus 1 cos squared theta, which is that bit there, which I can do quite easily. What's next? Where else is beta coming up? Beta comes up here. Where is it? It's in the middle of all this crud, isn't it? So it's a half h squared sec to the 4 to the minus 1. Is it plus or minus? It's plus. Plus 1 half. This is the determinant of the metric tensor, sec squared theta, all to the power minus 1, times, I'm just looking at the beta component. What have I got? That term's an alpha, that's an alpha as well, it's beta. Di by di theta of h sec squared to the 4 is this one. Oh dear. So it's 4h here, 4h squared sine sec to the 5. Good grief. 4h squared, what was it? Sine sec to the 5. Sine theta sec to the 5 theta. You see there's a sec to the, oh, it's x squared sec to the 4, isn't it? 4 theta. Where was I? We differentiated with respect to theta, h squared sec to the 4, and got this monstrosity here. And we've got a plus beta h to the minus 1 cos squared times beta h minus 1 cos squared theta. And this had better be equal to 0 as well. Equals. Let's think about the power of h. We've got an h to the minus 2 here and an h squared and an h minus 1. So everything's h to the power minus 1. So again, I'm going to subtract out or factorize by beta h to the minus 1 times the differential with respect to theta of cos squared is minus 2 sine theta cos theta plus, I've got the h squared, I can ignore the h squared. We've got a half, the factor of h has come out, cos to the 4 theta, which is that term there. Back to black. Oops. Back to black. Times 4. The h has gone. The beta has gone. I say gone, it's factorized. Sine theta, which is that term there, and what have we got? We've got a sec to the 5 cos squared sec cubed theta. My goodness me. Oh, mind you, it's coming together, equals beta h minus 1 into minus 2 sine theta cos theta plus 2 cos to the 4 sec cubed is cos theta times, sine theta there. Oh, the s is the wrong place. I'll just write that again. Sine theta. Hey. And they all cancel. How about that? Right. Recap time. What I had was in my peculiar h theta coordinates, I had a vector field which was constant because it had constant components in Cartesian coordinates. There it is, alpha and beta. And then I went through an enormously complicated process of transforming this contravariant vector, which was v vector equals vh plus v theta e theta, calculating these things here, and then I wanted to work out what would be called the divergence of v in Cartesian coordinates, but in tensor notation it's v alpha comma alpha, or sometimes you put the semicolon, which equals di v alpha by di x alpha plus the correction term alpha beta v beta Then I used to express that, I used the fact that there's a half g minus 1 di g by di x beta. Expanded in terms of beta, because we're summing over beta, went through all this nightmare process, and we got a whole bunch of stuff which was equal to 0. So, a recap of the recap. A constant vector field has 0 divergence. You might not be terribly impressed by that, and I wouldn't blame you if you started complaining that I've gone on for nearly a whole hour to show that a uniform vector field has 0 divergence. But it's not going to be long now before we're going to move off or move away from or progress from flat spaces. And if our ideas don't work in flat two-dimensional space, they haven't got a Welch chance in a supernova of working near a black hole. So we've got to go through this stuff just to make sure it works. And as far as we can see, it does. I'm going to stop there. I'm pretty pleased with that. Stop.